Hello, everyone. Welcome to our Mobile Mapping Monday series. In our first two sessions, Jason walked us through the basics of mobile mapping and showed us how to get a jump start on becoming a pro through post-processing. Today, you'll learn how to master the skill of fine-tuning MMS data. I'm Christine Grail, and I'll be the moderator for today's session. Our presenter today is Jason Ellis. Jason has nearly 20 years of surveying experience, including more than 15 years working with laser scanning. A creative thinker and technology advocate, Jason has spent much of his career in leadership roles, such as technology director for the Klingers Group and business development manager for TrueScan 3D. He currently serves as mobile mapping service and support specialist for Leica Geosystems, a Hexagon company, where he focuses on helping companies successfully implement and develop mobile mapping services. We encourage you to ask questions during the webinar. You can simply type your questions into the questions box, which you should see on the screen. On the line with us today is Josh Rayburn, Mobile Mapping and UAV Manager for Leica Geosystems, who will be answering your questions behind the scenes in today's session. And with that, I'm going to go ahead and turn it over to you, Jason.
Thanks, Christine. Appreciate it. I appreciate everybody taking the time to join me today in the third installment here. And I just want to take a moment to talk about what we have already discussed. So far in this series, we've talked about the core concepts of mobile mapping. We've discussed the anatomy of a trajectory and the various hardware components of a mobile mapping platform. We reviewed the benefits of mission planning and different considerations in the field when it comes to safety and productivity. We discussed field collections and even watched a field collection video. Now, last week, we started to get more technical with the review of post-processing data in Pegasus Manager, which is our all-in-one production and analysis mobile mapping solution. So as a refresher, we discussed how the automatic processing module can easily produce unadjusted LiDAR and images, as well as deliverables, to be reviewed in the office or in the field. Now, unadjusted data is great for asset inventory and GIS type applications. Projects where the accuracy requirements are not as stringent as, say, a roadway design project. But what if we have a roadway design project? How do we dial our results in further to meet high accuracy standards? The trajectory adjustment module in Pegasus Manager answers that question. And that's what we're going to be looking at today. The trajectory adjustment module, and more specifically, the multi-pass workflow. So the multi-pass adjustment is serving two purposes at once. It's improving our relative accuracy and our global accuracy. So relative accuracy we can think of as our cloud-to-cloud accuracy. How closely do overlapping data sets match one another? And our global accuracy we can think of as where in the world is this data resting? How close is it to actual known points on the Earth's surface? So multi-pass brings two or more overlapping LiDAR data sets together to appear as one, and then adjusts everything to our survey control. Our automatic tools will streamline this process. So in this example that I'm sharing with you, you can see that in this cross section of our LiDAR data, we have about 1/10 of a foot of separation. So these are two separate passes. One is green, one is blue. Now, this separation is typical when we look at unadjusted data. We will often see some separation horizontally or vertically. And it's this tool set that's going to try to iron those wrinkles out of the data itself. Also, when we compare data to our survey control, it's possible that we see some separation from our survey control to the actual LiDAR itself. In this example, you can see that Horizontally, our survey control point looks pretty decent, but vertically, we've got about 1/10 of separation here as well. So in order to address these two issues, we're going to use this tool set called multipass. And the first step in multipass is what we call multipass detection. And basically what we're doing here is we're telling the software to look at two separate tracks. So in this example, we have track B and track C, and we can think of these as just overlapping LiDAR data sets. So we have these two tracks, and we're going to input some stationing information. We're telling the software where to look at these two tracks or how to look at these two tracks. And after it runs the automatic detection, it's going to show us where it has found potential relationships between those two LiDAR data sets. It's basically showing us that, hey, I think I found something at this location, so on and so forth. So in this particular example, the software has found about 66 potential overlaps or links, and we're going to go to the next step, which quantifies the validity of each one of these. And this is called multipass measurement. So what multipass measurement does is it validates and measures the spatial difference or the delta in the XYZ for each detected link. So every one of those 66 links that we saw in the previous slide, every one of those will be looked at independently to try to score or validate how well the data matches one another at that location. Now, after we measure with the multipass measurement tool, we get an opportunity to review whether or not those links were valid or invalid. So in this example here, you can see that we've got a ton of blue or valid links, but we did end up in this location, we have an invalid link. And basically what this means is, for whatever reason, the software didn't find a good overlap or a good candidate for a match here. And it's just letting us know, hey, in this area, we don't have an automatic link that is valid. So we have the opportunity at this point in our workflow to specify a link manually. We call this a multipass manual link. And with a multipass manual link, what we're basically doing is we're telling it a point on a track is the same as a point on another track. We're doing it's almost a cloud constraint. You can think of it that way. So for example, we have a turn arrow here. We could say that the turn arrow in track B, the point of that turn arrow is the same as the turn arrow in track C, or we could use striping. So anything that occurs in more than one overlapping track, you could dial in as a manual link. Let me try to illustrate that a little better for you. So in this example here, you can see that we have a ground control point. So I can manually pick the tip of that point from the first pass, and I can manually pick it in the second pass, and I can basically tell the software that it's the same point. So along this trajectory, I see that point from this location in time, and along this trajectory, I see the same point at this location in time. This is a manually picked point. Now, we also have the option to use a tool set that we call ground target recognition. And what this is going to do is allow us to use our ground target locations and have the software go through all of the data and find our ground targets and use them as manual links to constrain overlapping data sets together. So the basic workflow is we feed the software survey coordinates. So we've gone out ahead of time and we've picked up the XYZ locations of our ground targets. We feed it a file along with a template file. So this is a DWG file that has the same dimensions as the target that we would have laid down in the field. And then we tell the software, look at these two tracks, go to each one of these locations, look for this template, and when you find it, fit the template into the LiDAR. So do a best fit of that template onto the LiDAR, and then set a point or calculate a point right on the tip of that DWG template that we fed it. When it sets that point, what it's going to do is take a measurement from the point that it's set to the XYZ coordinates that you fed it at the beginning of this exercise. So it's going to measure from the tip of the CAD template to this XYZ, and it's going to give us the difference or the delta in the X, the Y, and the Z for every one of our control points. Now this is going to end up serving two purposes. In the original context that I was talking with you about, it's going to resolve our relative accuracy. It's going to help resolve our relative accuracy. It's going to bring two or more overlapping tracks together. But we can also use the same information to do a constraint to our survey control. And it's all done in this multi-pass workflow. So we don't have to have a special operation for global accuracy. We're able to just roll both of these adjustments into this one multi-pass workflow. So let me go ahead and move forward. This is going to bring us to the actual adjustment itself. So every automatically detected link that the software found, every manual link that we specified, and every manual link that we used our ground control to specify, all of those are going to be individual records in a table that we use for the adjustment. And you can think about it as building a case for the adjustment, okay? Now, when we run the adjustment, basically what we're telling it is use all the features that we've already specified. So use all of the records that we've populated into our adjustment table. Use the ground control points to constrain the entire data set to our survey control. Also, automatically remove the outliers from the records that we fed the software. So basically what's happening is all the records that we specified during the previous steps, it's going to disable one at a time and recalculate the deltas in the X, Y, and Z until the separation in the X, Y, and Z has an average separation of 1 centimeter or better. Okay, so we're targeting 1 centimeter of separation in the X, Y, and Z or better. And when I say or better, it doesn't mean that once it hits 1 centimeter of separation, it's going to stop. It's going to keep going till it can't squeeze anything else out of it. But this is our target here. This is a 1 centimeter threshold. It does all this very quickly. In a matter of seconds, it goes through all these records, recalculates the trajectory, determines what your mean values are, your mean residuals are. And once it completes, we have an opportunity to update the trajectory. So when we update the trajectory, this is going back to the initial session that we participated in together when I talked about the snake skeleton, right? I talked about how the skeleton of the snake we can think of as the trajectory, and the ribs of that skeleton we can think of as the LiDAR and the images. And anytime there's an adjustment to the shape of that spine, all the ribs are going to move with it. Well, that's really what's happening with the trajectory adjustment. We're updating the trajectory based off of its position relative to known points. So we're going to update that trajectory. We're going to generate a new trajectory. And then we're going to update everything that's attached to it. So when we hit update trajectory, we take that new trajectory back to our automatic processing module and we import it. So we're basically saying, hey, we have a new version of the trajectory now. Let's rebuild our image orientation and our 3D point cloud to match it. And then finally, this PegTrax is like a line shape file that matches the trajectory as well. So when we run this piece of this part of our workflow and go back and review our results, you can see that before multipass, before this trajectory adjustment, we had about 1/10 of separation from track to track. Okay, our relative accuracy was off. But if you look at the animation here on the right, you can see that after multipass, we've closed that up. We've resolved our vertical and horizontal separation. And as a result of that same workflow, we've done the same thing with our survey control. So prior to the adjustment, we had about 1/10 of separation from our survey control. And you can see from the animation on the right there that those red points are now falling directly on the point cloud vertically, which is great visually, right? So visually we can see this and everybody feels good about it when they look at it, but we really need to quantify what we've done, okay? So when we are talking about ground target recognition, when we talk about this workflow, when we feed it survey control points and we feed it this template and it goes through our data and it measures these differences, we can create a report from this information. So this delta XYZ, this is the degree that we are adjusting our data to match our control. And we can run this ground target recognition and generate a report before we actually execute the adjustment, and we can do it after we execute the adjustment. So we can come back in here, use this tool set after our adjustment, come up with a new set of deltas or a new set of separation values here, and generate a report that includes this information, right? So it's important to have a paper trail for whoever you're submitting your data to. You know, if it's internal work, you're working for an engineering department, or you're working for a DOT or maybe a municipality, they're probably going to have a keen interest in how well you did initially. So your unadjusted results, how close were you to your survey control before you did anything? And how did you do after your adjustment? So we generate these two types of reports from the data that captures all that information, so that you have a digital paper trail of your efforts. So you've got something that looks like this, where you've got your, hey, this was my raw data, and here are my statistics for my X, Y, Z, and 3D. And after we did the adjustment, I can generate another report and show, here are my statistics. And you can compare column to column and see on this example project that I've been sharing with you that we can demonstrate where we started and where we ended up, and that there was in fact a significant improvement to our data. So that is generally the we have other tools in the trajectory adjustment module for smaller kind of niche scenarios, but the multipass workflow is the bulk of our adjustment tool set, and it's something that we're very excited about and is consistently a reliable solution. So I appreciate you taking the time to look at it with me today, and I'm happy to take any questions that you might have.
Thank you, Jason. Just a reminder to everyone who's on the line with us, you can enter your questions in the questions box and we will get to those. We do have one about automatic ground target recognition. Do you have the ability to only do control points, or can you do validation points also, is one of the questions that was asked.
No, that's a great question. Sorry, I'm turning my camera on here to be consistent with the
Excellent,
other
thank you.
sessions. You can do it both ways. So when you run the automatic detection, the results that it's measuring can be classified as either a control point or they can be classified as a verification point. And this is a great question because anything that's classified as a verification point will not be used for the adjustment itself. It'll be ignored by the software. So you can run ground target recognition and come up with, everything can be in the same table, but they'll have different IDs based on the type of point that they are. If it's classified as a control point, it'll be used for the adjustment. And if it's classified as a verification point, you can just use it for a report. So if you had to have an independent verification check, you could do that. Great question.
Okay, good to know. In what you showed before, were you showing a least squares adjustment? Can you
Yes,
clarify?
yes, it's a least squares adjustment.
Okay, excellent. Can you use multiple template styles in the same project, is what someone else wants to know.
For the report itself, we have basically the two reports are either Excel, so you get an Excel report, kind of like we looked at in the last slide there, or you can get a monograph report, which is basically a Word document. So we currently don't have templates that you could preload, but you can manipulate everything in either one of those reports from a visual perspective. I don't encourage you to manipulate the data, but from a visualization perspective or a formatting perspective, you've got a lot of freedom within what Microsoft's providing in Office.
Okay, and we have a clarification here in terms of that question, and that is with regard to the auto target recognition, not necessarily the reports.
Oh, I'm sorry. Yeah, so we have some preset recommendations on what those templates can look like. You don't have to use the 90-degree chevron that I showed in my example. But yeah, we do have some other templates that you can work with, and there's some flexibility there for sure.
Okay, excellent. Now here's a great question. What happens when you lose your GPS signal? What would you recommend doing in that case?
Yeah, so this isn't uncommon. Especially if you're doing collections in warm weather where there's full canopy on trees and things of that nature. And it's one of the reasons why our mobile mapping platforms are equipped with both the GNSS and the IMU. When the GNSS cuts out for whatever reason, whatever the obstruction is, the IMU is going to carry that position and heading very reliably for X amount of time. So in most collection scenarios where we're doing residential work or highway work, things like that, it's not an issue to lose the GNSS for a few seconds or 10 seconds or 20 seconds. When we come out of that obstruction, when we come out from under that obstruction, we're going to regain GNSS, and that position from the GNSS that was regained is going to be backwards calculated in time as a correction to the trajectory. When we post-process trajectories, we post-process it both forward and reverse in time. So we have an opportunity when we come out from underneath an obstruction to take that position and reverse apply it to our trajectory as a correction. Now, if we know that we're going to be without GNSS for a considerable amount of time, like if we're doing very long tunnel collections or something to that effect, then we can plan for that by including a wheel sensor with our collection. And the wheel sensor would basically be supplemental straight line information that we can apply to the trajectory to work in concert with the IMU data.
Okay, thank you, Jason.
Sure.
Um, we do have a clarification question too, and we were talking about target templates. Is it possible to use control points only, only points measured by GNSS, or do you have to use a template?
You can use them as a vertical, but in order for, so to be clear, if you were to go out and pick up points with the GPS, um, you would have those points, and assuming that we projected our mobile data into the same coordinate system, they would be very close to one another. And you could use those control points as a vertical constraint, right? But in order to also use them as a horizontal constraint, we have to be able to see what they were set on in the LiDAR. So the nature of LiDAR, as you know, is millions of points in one profile after another. So it's almost it's a mosaic of points. And when we zoom out, we can make out a lot of detail in LiDAR. But if we zoom in and we're looking for, like, what are the chances, we're not going to be able to discern a magnail or a small spray point, most likely like a paint point, um, in the LiDAR. So, if we're really concerned with our horizontal accuracy as well, if it's important for the project, we're going to plan for that, and we're going to make sure that we lay things out in the project in the form of a target of some sort, so that when we make our adjustments, we can have full confidence that we are not only satisfying our vertical, but our horizontal as well.
Okay, great. Thank you. We do still have some questions to get to, but before we continue on that, I do want to make a quick plug for our next session in Mobile Mapping Mondays. Jason, I think we have a teaser slide there that we can
Oh,
show.
drive.
Just want to mention that we will be taking a break next Monday in observance of Memorial Day, but you will want to join us on Monday, June 1st, as Jason covers the next topic in our series, a fast new way to create striking MMS deliverables. You don't have to do anything else to join that session. You will automatically receive an email reminder and log in, but I do want to encourage you to participate live in that session. So Jason, we do have a few more questions that we want to get to today. One of them is, in the process that you showed, how much of that process is automated and how much of it requires a technician to manually complete?
So in the first step that I showed, automatic detection, it's interacting with the dialog box, punching in a few variables and hitting process. And then from that point forward, it's automated. It goes through, it finds all the automatically detected links. Um, when we go to the next step, which is multi-pass measurement, where we're validating each one of those links, that's automated as well. So we hit one or two variables and we hit process, and then it goes forward and does all the thinking for us. And then it's at that point where we make a judgment call and we say, am I satisfied with the automatic detection results, or do I feel that, maybe over here in this intersection, I want to manually define a point and say that this is a common point between two or more passes. Then we would manually set those 2 points, which is fairly easy to do. I probably wouldn't want to do 500 of them, but if you had to do, a dozen or so, it's not that big of a deal. Um, and then once those are defined, you can go ahead to the adjustment, which again, you pick a couple of variables and then hit process. So it's a semi-automated process, but the actual user interaction with each one of those steps is very minimal. It's less than a minute to plug in what variables you want to roll with. And two of those four processes are they're very fast to compute as well, like 10-20 seconds fast. Um, so it's very useful. When I first got into mobile mapping, we didn't have anything like that, and to be where we are today is light years away from when I got involved. And it's really just a fantastic productivity leap forward. And it's very easy for most people that are used to working in CAD and, surveying programs in general, especially laser scanning. It's just a very easy thing to transition to.
Okay, excellent. Now, with regard to the multi-pass process, can you run multiple iterations of that process or add additional links to continue tightening up the solution?
You can. So when you look at the results, if you see that, oh, hey, I got to the end of this and I see that I still have a tenth in this one area that, I missed, or the software missed, or whatever the issue is, you have an opportunity to fine tune it. And I kind of made a little mention of this at the end of the presentation. I said we have some other kind of niche adjustment tools. And that's where these would come into play, where you're going to have a menu of a few other tools that you can use for special situations, where you can say, 95% of my project looks good. I'm almost ready to go to deliverables, but in this area right here, I really need to tighten it up for whatever reason. You've got some tools at your disposal to do that rather quickly.
Okay, great. What plot must be considered NIE to determine whether the data is good or not?
Well, I'm sorry, what was the question?
What plot must be considered
Well,
NIE to determine whether the data is good or not?
oh, okay. Yeah, so NIE, so the question centers around inertial explorer, which I talked about in the last session. So in the last session, we talked about nav prep, or navigation preparation, and how what that is it's solving the trajectory for us, right? We're feeding it a base station and we're feeding it Pegasus data, and it's going to resolve that trajectory for us. Well, the question is, how do we determine the quality of that trajectory specifically, the question was in Inertial Explorer. So us using Inertial Explorer in the background of NavPrep allows us to go into Inertial Explorer and use some of the quality plots. And they're asking what plot is an indicator of a good trajectory. Well, there's several. There's not just one. Your analysis of a trajectory is kind of a conglomerate of everything that you're looking at in Inertial Explorer, but a couple of go-to ones that I will look at if I'm using Inertial Explorer, and I'll come back to this in just a second. But if I'm using Inertial Explorer to analyze the quality, I'll look at the estimated positional accuracy. So that's the first plot that I would look at. I would look at the combined separation. So this is telling us how close our forward in time and our reverse in time trajectory solutions match one another. I would look at those two. I would look at satellite bar. I would look at the GPS and IMU positional misclosure. So these are all handy plots. And the more you can look at and the more you can understand each one of those plots, the higher your confidence is going to be when you have to do a deep dive into trajectory quality in Inertial Explorer. That said, in Pegasus Manager, when we use NavPrep, which is Inertial Explorer Lite, we can think of it as that way. When we run NavPrep, we're generating a shapefile called the QF shapefile, quality factor shapefile, and that's generated in your mission, and it's saved in the GPS INS folder of your mission. You can load this in, you can review it, and by looking at it's basically a point shapefile that scores your trajectory through the whole collection. It's a series of points that are either red, yellow, or green. Green is good, red is bad, and you can get a feel for, and there's numbers that go with those values, but you can get a feel for how well you did on your trajectory just by looking at that QF shapefile. It's easier than going into IE, but IE is always there as your secondary parachute if you need it.
Very helpful tips. Thank you. We have a question here about multipass adjustments. If you have 4 overlapping tracks, will it adjust them all together, or is it only comparing 2 of them?
It will try to fit all 4 of them together. So it will look for overlapping data in all 4 tracks. If you let it run on all 4 at once, it's going to try to fit them together. Now, depending on how your project is laid out, um, if you're doing road work or if you're doing a parking lot, say for instance, the way that you collect the data may dictate how you point multipass at your project. So there's not one answer, but generally speaking, if you have 4 overlapping data sets, it's going to try to squeeze them all together.
Okay, great. Now, what you've showed us over the last few weeks in terms of the workflow for mobile mapping, specifically using the Pegasus solution, it looks like it's pretty seamless. So how long on average would it take to train someone to become efficient and confident in both collecting the data and processing the data to ground control? What kind of expectations should we have there?
Yeah, so field collection itself is, as you saw from the video last week, if you could join us, the field collection is pretty simple. It's pretty straightforward. Um, the biggest thing about a field collection is to make sure that before we go do we talked about this in the first session, before we go and do a collection, we want to make sure that we've considered as many factors that might derail us during our collection. So we need to have a plan for every mission before we go do the work. We don't want to figure it out while we're in the car. But to actually teach somebody to activate the MDA and collect the LiDAR and the images, deactivate and download that data to bring back into the office, I usually can have that taken care of in an hour or 2. Now, invariably, there will be questions over time. Somebody will forget something or they'll encounter something that was unexpected. And that's what support's there for. But generally speaking, we can plug somebody into field collection very quickly. Now, when we do training for new customers, we plan to spend up to a week at that customer's office. So we go through field training, we go through post-processing, and what you just saw in this presentation, which is adjustments. And we'll do that multiple times throughout the week until we get to a point where we feel that you are comfortable with the essentials, which is field collection, looking at unadjusted results, so verifying, hey, we have LiDAR and we have images, we're good, and then adjusting to survey control. So typically that takes about a week or so. And then after that training, we have a series of virtual interactions that the customer would be entitled to reinforce what we went through the first week and to try to file some of the rough edges off of things.
Thank you, Jason. It's all about making it as easy as possible, isn't it?
Absolutely. Yep.
All right. Well, I think I'm going to ask you to put your contact information back up on the screen for anyone
Okay.
who would reach out to you. I do recommend at any point, if you have questions, please do reach out to either Jason or Josh. You can connect with both of them on LinkedIn, and I believe both of them are on Twitter as well. So feel free to connect with them on social media. This does bring us to the end of today's webinar. Again, I do hope you can join us on June 1st as we wrap up this series with an exciting presentation on MMS deliverables. So please do join us for that. As you exit the webinar today, please fill out the survey that should pop up on your screen. We appreciate your time and hope you found this webinar to be a valuable experience. Thank you, everyone.
Thank you.